thanks, Dick, for the wonderful introduction, and also for the, you didn't explicitly say it, but for the postdoc mentorship that I got from him when I came here as a postdoc at 1983. This always inspired me in the, when I mentor postdocs. It was a great period for me personally and for my research to be here as a postdoc, especially with Dick. So I want to talk to you tonight about randomness. Randomness is a topic that in some sense is very easy to talk about because different people of all walks of life and in all ages. I actually had a nice conversation with Wesley here earlier on, have ideas, opinions, feelings about luck and chance and probability and uncertainty, all sorts of words that are related to the notion of randomness. That's okay. And because of this, it's at least a good topic to start talking about. Then, of course, things diverge because different people have different feelings or opinions about randomness. It's a topic that was discussed for millennia for many reasons and by many groups of people, both scientists, mathematicians, and philosophers. Many gave in different fields, different definitions were given, theories of probability, theories of entropy in physics. And what I want to talk about today is, the computer science view, the complexity theory view of randomness, how we think about it and what this way of thinking gives us. So let me tell you how the plan of the talk is going to be. Please stop and ask questions if anything is unclear, you want to, or any comment. So I want to first talk about perfect randomness, just to set, the field straight, the basic language straight. So I'm going to talk about only about discrete events, and the basic random event is going to be, for me, a coin toss. There are two possible outcomes, heads and tails, and I want it to be a perfect coin toss, so the probability of each is 1/2. Okay? And then you can repeat it. You can repeat it any number of times you want. When you repeat it, the outcomes are independent of each other. That would be, for me, the perfect random events, just sequence of coin tosses. And just to make sure you are all with me, here are the outcomes of two 20 sequence tosses. Which is more likely? All right. So I heard some with different opinion, but I think the consensus is that they have the same probability. And that's what you should think about. I mean, if the chance of every coin toss is 1/2, then when you toss it 20 times, every particular sequence has a chance of 1 in 1/2 to the power 20, which is roughly, I guess, 1 in a million. Anyway, they both have equal probability. And so sequences like this, every sequence you write down of the same length has the same probability. That's perfect. That's what will be our goal or our desire, or the assumption under which things we will do will work. Okay? And I'll give you lots of, sometimes it's called the uniform distribution over sequences or the full entropy distribution. And I will give you lots of amazing things you can do if you have this available, if you have such perfect randomness available. Okay? And the main question we'll ask ourselves is, are all these consequences that actually are used in real life, are they real or just a figment of our imagination? Because after all, where do you get perfect randomness? So this will be the next issue to address. And for this, we'll have to understand haystacks. and what we will call and define pseudo-randomness. So basically, it's the study of deterministic structures that somehow have something in common with random structures. And I'll define it, and I'll show you for this too also why. I have to be closer. Examples and applications of this. And then at the end, I'll talk about what I mentioned in my abstract, what can we do if we don't have perfect randomness? What do we do if the world has no randomness at all? I mean, all these wonderful applications, do they survive or not? So we'll get to this at the end. Okay, so let me start with examples. The first example, so some you'll be familiar with, and some maybe you will not be so familiar with. Some will be clearer than others, but I hope to give you a sense that there is a wealth of applications if we have access to perfect randomness. So I'm sure the first you are familiar with. Oops. Yeah, this little cartoon I'll show you on every slide, because I want you to think, whenever you think, wow, we can do this with randomness, where do we get it from? So getting information fast, somehow this is more, elections are more, on everybody's mind today. We have 3 million people, and we want to know, they each have an opinion. It's either red or blue, whatever that means. And we want to know what they think. If there were elections, that would be their vote, who will win, red or blue? 3 million votes is a lot of people. So one thing we can do, if we have perfect randomness, is to pick a random sample and just count how many reds and how many blues are there. And so here is a random choice. Let's say we pick 2,000 people at random, completely at random, if we have randomness. Then it's an amazing property. It's an amazing, I would say it's one of the most amazing theorems of mathematics, and certainly one of the most applicable ones, that you can tell how accurate will be this sample with high probability. So in this case, if I pick 2,000, it turns out with the probability 99%, the sample will be accurate up to 2%. So the number of reds in the sample, in this small sample, and the number of reds in the whole vast population will be within 2% of each other, except with probability 0.01. Okay, so I wrote it again in different words. All but 1% of these subsets will be bad, will be inaccurate, will be off by more than 2%. And this is amazing in itself. It's even more amazing that this sampling property does not depend on the 3 million there. It just depends on the fact that we picked a set of size 2,000. If instead we did it in China and 1 billion people were voting, it would be the same thing. If every star in the universe was voting, it would still be the same. So 2,000 sample will give you a very accurate thing if you have perfect randomness. Now, this is if you have randomness. What if you don't? Well, if you don't, then, so you have to deterministically do something. And you don't know, you never know whether you started maybe with the red contingent. Maybe they're all on the East Coast or something. Basically, if you did it deterministically, you would have to go and ask everyone. And there's a vast difference in the amount of time you'll need to count 2,000 and to count everyone. So that's a very powerful demonstration of what you can do with randomness. Sampling enters in lots of applications of randomness. So I want to give you now some others. Yeah. This is a very different application. Looks like a toy. So what do we see on the board? We see a square, like a grid of squares, and a domino tiling of it. Dominoes are 2x1 squares, 2x1 rectangles. So this is a particular way to cover this region with dominoes. And here's what we want to know. I give you a region, it doesn't have to be a square, just a large region in space, and I ask you in how many ways can you do this domino tiling? You can see the domino tiling, this is a particular one, and you can see that you can imagine that there are many others, in fact, exponentially many. And the question is, even I gave you just 100 by 100 and asked this question, well, I challenge you to think about it. So that's the question. And the interesting thing is not just a toy or a game. This is a fundamental problem in physics. It's called the Daimer problem. And if you understand this, the answer to this, if you can approximate this number, you understand fundamental properties of matter, that's diatomic material. It calculates for you things that have to do with energy and phase transitions of this material. So it's really important to be able to do that. And the question, so people studied it. They want to be able to approximate this vast number. And with access to randomness, these people invented a very fast algorithm that approximately counts the number of domino tilings. This algorithm is one from a family called Monte Carlo methods that I'm sure some of you heard about, was invented by von Neumann and Ulam initially for the Manhattan Project. It's a very sophisticated algorithm. It's not like the sampling we saw before. Proving that it works is extremely difficult. And, but anyway, it works. So when people are using it. And so the question is, what happens if you didn't have perfect randomness? How would you run? So when I say probabilistic algorithm, you just should think of a computer program, like a normal computer program that is allowed to make decisions, some of its decisions randomly. Sort of can toss a coin on the side. If we didn't have it, the best deterministic algorithm that we know, so algorithm without randomness, runs in exponential time. Exponential time you should think of like infinity. It will take billions of years even just to solve this particular problem. At least as far as we know. So I am stressing here, that's the best known algorithm. Here, it's possible that someone tomorrow will come up with a faster algorithm. We don't know. But currently, there's a huge gap between what can be done with randomness and without randomness. And this is just an example of one probabilistic algorithm. There are numerous others. They, they exist in basically all areas, in all sciences. You see them in industry. They are used. Well, I'm sure they are used also in the military and in economic, even in financial companies. They are used everywhere. They're used for simulations, and they're used everywhere. And in all of them, this same feature occurs, that they are very fast. And without them, for all these problems that I didn't mention here, but they exist for all these problems, the best known deterministic algorithms are very slow. They are exponentially slow, require exponential time in the size of the data. Okay, so that's another demonstration. So these probabilistic algorithms are a huge field, and they also demonstrate the power of randomness. So here there's a gap between, there's an exponential gap, a vast gap between what we can do with and without randomness. But in fact, there are other applications where the gap is infinite. There are things that can be done with randomness and just simply cannot be done otherwise. So let me tell you about this. You don't have to read everything on the slide. I'll look at the pictures. They are much nicer. So we switch to a different area, distributed computing. Distributed computing is a field that studies interactions of large systems of participants. And it focuses on situations where there is no synchrony, there is no common clock running the thing. So I can send a message to you and to you at the same time, and this will arrive in a second, and this will arrive, especially to Fred, will probably arrive next year. So there's no control on timing, so that really complicates matters. This is actually a realistic assumption for many systems, so you want to study it. And I just listed here two problems. One is called the dining philosopher's problem, and the other is called the Byzantine general's problem. From this, you can immediately infer that this is a field that knows how to pick names for its problems so that they are appealing. Computational complexity didn't do so well. In the first, these dining philosophers, their problem is really, as you can imagine, from the pasta dishes and the two forks on the side. It's a resource allocation problem. These philosophers cannot eat with one fork, they need two. So the question is how to arrange so that they get to eat, but none of them starves in this asynchronous, they get hungry at random, unpredictable times. The second, it's about coordination in asynchronous situations. The coordination, like a few generals have to decide whether to attack or retreat. It's very important that they will be unanimous. Maybe they send messengers to each other, but some of these messengers may get delayed. They can go to a pub, maybe, or they can be captured by the enemy. And nevertheless, they want to reach agreement. So in both, I'm not defining them formally, but in both of these cases, asynchrony presents a serious obstacle. And nevertheless, you can try to design protocols for these participants so that they achieve the goals. And in both cases, there are two types of theorems. One says that if these programs are deterministic, have no randomness at all, there is no solution whatsoever. It cannot be solved. And the other, in each, is that if they have randomness, if the programs are allowed to be probabilistic, then there are solutions. So here is a gap between just being able to do something or not being able to do it at all. Another demonstration of this power. Okay, so I will have two more such examples of fields where randomness is important. And the next two examples, actually even beyond what we talked so far of being able to achieve something, it's even for the purpose of just correctly defining a basic notion. Some basic notions that you've heard of, I'm sure, so let me tell you about both. So the first one is in the field of game theory. Game theory, microeconomics, is a study of rational behavior. How do people behave in strategic situations so as to optimize their profit, anything that they, in their set of preferences is highest. So this is a particular example. It's called the game of chicken, a chicken game suggested by Aumann. These games are presented as matrices of payoffs to the player. So in this case, there are two players. There can be more than two players. And in this particular chicken game, let me explain these numbers. So I guess there's a blue and purple players. And in each square, there are two strategies for each player. A is aggressive and C is cautious. So each can be aggressive or cautious. You can think about two companies who compete. If the row player is cautious and the column player is aggressive, does it work, this? Yeah. So cautious is aggressive, then the first player will get nothing and the second player will get $2. Okay? Anyway, this is the input, that's the data about the game, about the situation. And then the question is, how should they behave? What is the most rational way for them to behave? The reason it's called the chicken game, Aumann did it to depict this kind of situation, two macho drivers driving on a narrow road on a collision course, and each of them can be cautious, namely swerve and let the other pass, or be macho and continue straight, hoping that the other guy will swerve. That in this case, in this story, I guess this -3 should probably be -infinity if they are both. But that's the way you describe a strategic situation. It can be a much larger matrix with lots of strategies. There can be more players than two, and so on. And the question is, what is a good description of strategies for these players that will be rational? And the prominent definition was suggested by John Nash. And it's the following. It's a very natural stability requirement from the strategies. It says the following, each of them picks a strategy. This pair is good if, when I know your strategy, I have no reason to deviate from mine. And similarly for you. They are stable in which, given what I know about all the other players, what I picked, I'll keep. I have no reason to switch. So it's a very natural notion of stability. It certainly is rational. If some outside entity gave that strategy to the players, they would have no reason to deviate. That's the idea. But Nash didn't get his Nobel Prize just for this definition. He actually got it for this theorem that he proved, saying that it's a universal definition. It's not just something you wish for. It can be achieved every time, no matter how large the matrix, how many strategies, it doesn't matter. There is always a Nash equilibrium to every game. So it's a good solution concept. And the only twist is that this theorem, I didn't finish it yet, here's the end, is true if strategies are allowed to be mixed in the economic language or random in our language. So what do I mean by that? That players are allowed to choose a strategy which is with probability X do something, with probability of something, Y do something else. That's allowed. And in this particular game, it turns out that there is a unique Nash equilibrium, and in this equilibrium, it has to be mixed. Turns out with these numbers, you should be cautious with probability 3/4 and aggressive with probability 1/4, and then you will have no reason to deviate, knowing that the other is doing the same. So every game has such an equilibrium if you allow randomness in the definition of what a strategy is. And in this example and in lots of other examples, if you disallow randomness, then this concept loses a lot. I mean, there are lots of games for which there is no equilibrium. So here, for the very definition, you need this randomness. That's one area where randomness is essential. Of course, it's essential in many other theorems of the field. And another field where it's essential is cryptography and electrosecurity and electronic commerce. And here, the very basic notion is a secret. What does it mean for me to have a secret that you don't know? There's no way to define it sensibly without randomness. If I cannot toss coins to choose my secret, then, it's not a secret. This is one of the first theorems of the subject by Shannon, is that basically a secret is only as good as the amount of randomness or entropy in it. If I pick, like in this example, if I pick a 9-digit password completely uniformly at random using perfect randomness, there are 10 to the 9 possibilities. Therefore, the chances you guess it is exactly 1 in 10 to the 9, which is very low. But if I picked it instead from another distribution, where I pick it among the phone numbers of my friends, so, maybe 50, maybe 100, if you have Facebook, maybe 500, it's not very hard to guess your number. So you should have perfect randomness. Your secrets will be guarded better. And what is true about secret is true about all the many, many concepts in this field of cryptography, all the amazing things we can do with it that are so important for electronic commerce. So all of them require randomness. Without randomness, you cannot even define. Maybe I need randomness for this, and it will work. So that's another field where randomness is essential. And of course, there are many other areas that I'm not talking about, like where randomness is absolutely essential. At least it has to look random if we want, we want to try and go there and believe that that's what they do is what we think they do. Okay, so we've seen a bunch of examples of applications of perfect randomness, and now we need to get busy and understand where they come from, where do random bits come from. And I know some people in the audience who heard the talk more than once. So how do you know anything? How do you answer a question you don't know the answer to? You Google it, right? So I Googled it. I wrote, 2 random bits, and here's where you get them. What you'd guess. I mean, you buy them, right? That's where you get them. You buy them. You buy them from one of these. Actually, there are like 4 million results, and that's a few years ago. So there are lots of companies who will sell you random bits, claiming to be true random bits. And you wonder, of course, where they get their random bits from, right? So when you go and read their websites, and some get it from, radioactive decay, from atmospheric noise. These two from various photon quantum phenomenal effects. So they use somehow natural sources of randomness or seeming. And then you start wondering, first, are they really doing it? B, how do you test the quality of this? It's really interesting that people actually buy this, right? I mean, did anybody in the audience ever bought random bits? No. Yeah, but people do. Do you know who buys? Do you know who is buying this? This company is very popular. This chip is very popular. Who is buying this? Actually, casinos do. Casinos do. They use them for, I guess it's trusted, and they use them for. Anyway, so some people do buy, and I once had an audience member in a talk I gave a few years ago on the same subject, and he was an artist, and he said that he paid $1,000 to one of these companies because he needed to generate patterns on for a picture, that he was not happy with what the computer, the usual random generator on the computer gave him. Anyway, people do buy it, probably not a lot. So how do we know they are good? And what do we do if we don't have them? That's the next question we are going to answer. Questions so far? Everybody's happy? Yeah?
What does true random even mean?
Yeah, that's a very good question. So yeah, I'm not going to answer you, but I'm going to show you in the next slide something that will be like an answer. So you are welcome to, I need a victim, so you can be my victim. What's your name?
Moran.
Moran, okay. So don't worry, I'm not going to cut you up or make you disappear or anything like this. Well, I don't know how to, but we want to define true randomness, so we want to define useful randomness. And here's an experiment that will teach us something about it. This is an experiment that was designed here in Berkeley about 35 years ago by Blam and Mikhaly. Well, you see me and you here. I am there and you are there, and I'm going to toss a coin. Maybe. I usually request money from the audience at this stage. So I have this coin, and I'm going to toss it, and when it's in the air, just like there, you should tell me whether it will land on heads or tails, okay? And we'll do it 3 times. Now, actually, we don't need to do it. What I want you to tell me really is if we did it, I just tossed it, and it just leaves my fingers, what do you think is the probability you will guess it correctly? Aha. Yeah. Okay, good. So, yeah, I think everybody would be in agreement that that's probably the probability that anybody will guess the outcome. Okay, so this was one experiment. Let's do it again. But before the next experiment, I'm going to give you a laptop. Maybe you have one. Just imagine you have a laptop in your lap, and you have to do the same. You know, I toss the coin, just as it leaves my finger, you have to guess whether it will land on the floor, heads or tails. What do you think the chance you'll get it right?
You're tossing? Sorry, say that.
I'm doing exactly like before.
Okay.
I'm tossing the coin. As it leaves my finger, you have to guess what it will be on the floor 2 seconds later.
Same.
Same. All right? Yes? Yeah, I'll definitely pay you later. Okay, yeah, I think everybody would agree with that also. So now let's, do the last experiment. Now I'm going to give you not just the laptop. I'm going to give you video cameras that are trained on my fingers in all directions. And I'm going to connect them to a Cray supercomputer. And this supercomputer is connected to your laptop. And you can use this equipment any way you like. And still, I'm going to toss the coin, and just as it leaves my finger, you should guess what it will be. What do you think are the chances you'll guess it right?
Still half, because it's not going to work.
Well, let's assume just for a second that it works. Maybe you have the help of some of the computer experts here.
Well, probably more.
More, yeah, I also think more. It depends really, you're absolutely right that it depends on the quality of the equipment, but what is there to calculate? It's not that complicated. Physics is understood for coin tosses. You have to be able to calculate, the force I apply, the momentum of the angular momentum of the coin as it leaves my finger, the distance to the floor, the humidity in the air, I don't know, the heat generated by the people here, but, you know what computers can do in split second today, right? So it's, it will be, I think, it will be very close to 1. So here's the point. Here's the point. Notice that I, the person who tosses the coin toss itself, what supposedly is the random event, did not change in these 3 experiments. They didn't change. The only thing that changed was the observer. So that's the main point of this talk. So randomness, this is a computational view, the computer science view of randomness. That randomness, how random some event is, how predictable or unpredictable it is, depends not on the phenomena itself, but, well, it depends on the phenomena in particular, but also on the computational power of the observer. It's a very different definition than the definition used in mathematics and physics. It's a subjective definition, depending on the observer. And it is with this definition, working with this definition, that we can understand the power of randomness and actually the limits of the power of randomness much better because of, well, as you will see. Okay, so questions about this? That's a very important message.
I have a question.
Yeah.
In the quantum world, maybe this is not true.
Yeah, okay, very good. So we'll get, maybe I can answer you now or I can answer you later. I'll say now, this can be done with the quantum world. It can be done anywhere. You have to remember, one thing to remember that people who, of course, this is one of the most common questions one gets. There's a tendency to confuse physical theories and reality. Physical theories, like quantum mechanics, predict that there is perfect randomness. They predict it. So physical theories, not all physical theories are correct. In fact, we'll never know if it's correct. But the other thing is, when implementing anything, any physical device that's supposed to recreate coin tosses, it's not going to be the quantum theoretic mathematical model. It's going to be some device like the laptop, right? And it's going to have some, it's going to measure photons, their spins, and so on. But, the spins, the photons have to be generated, the measurements have to take place, and they are happening with maybe some inaccuracy, maybe some things you can pick up with very good devices, like you can pick up my, microintos. So that's the short answer. Yes?
So it looks like to me you've gone from the probability of the event, which hasn't changed, right? It's still
Yeah.
tails, to the probability of predicting what will happen.
Very good. So I'm much more interested, much more interested. I don't really care about, of course, it's a prerequisite that there will be some chance of the event to be heads and tails. But what is more important for all the applications I'm going to discuss, and all the applications you've seen in the previous slides, is the prediction ability of any observer, in particular the algorithms using the randomness. That's the important thing for, for understanding the power of randomness in applications.
So is it possible for any receiver of the randomly generated bits to tell whether this is generated randomly, or like true randomly or false?
That's a very good question, and the short answer is no, but there is a positive answer with a little bit of help. And these are very recent results, and they are not in my talk, but I can answer this question in more detail later. To know whether something is random from a sample is impossible. I give you, just like you said in the first slide, heads, 20 times. And I ask you, was it generated randomly, or did I write it down because I wanted to? There is no way to tell. There's a great play by Tom Stoppard that some of you may know called Rosencrantz and Guildenstern Are Dead. How many people have, know this? Okay, yeah. It starts exactly with that. I mean, the two people are sitting, tossing coins, and it came up heads 80 times, and they discussed the chance it will come heads again. Anyway, okay, so we are digressing. Let me go back. I want to talk about pseudo-randomness. So I want to now go back to, eventually get to the hay and the haystacks I talked about in the beginning. And I'm going to tell you about this notion, pseudo-randomness like it sounds. It's something that should be like randomness, or as good as random. And in order to understand it, we have to understand properties of objects that look like, in some sense, they look like random properties, or they are properties of a random element of a universe. That's what we have to understand in order to understand, the questions of the applications I discussed before. It may not be clear in the beginning. I'll just get to it at the end. But for now, so this is a pretty abstract slide, but trust me, if you don't follow it, there will be lots of examples. So, but I want to describe what the study of pseudo-randomness is in generality, in abstract. So it's a study of universes of objects. Like the objects can be, of various types. They can be numbers, they can be sequences, they can be graphs, they can be tables or walks or codes or lots of, objects, mathematical objects of various sorts. So there's a universe of them. And then in this universe, here's the universe. And in this universe, there's a large subset, almost all of it, of elements that have some property. So it's what I'll call a random-like property. This is P. P is a subset of the universe, and this is the hay in the haystack. So almost everything has a property. So I wrote it in several ways. This property P is shared by most elements of the universe. Again, you'll see examples. This is like a hay in the haystack. And if you pick an element at random, if you have perfect randomness and could pick an element from the universe at random, almost surely it will have this property. I want to call any property like this a pseudo-random property. Of course, which property you pick is important for which applications you want to use it. And I want to tell you about two questions regarding this situation. It turns out mathematicians and computer scientists ask different questions, they're very related about this situation. Mathematicians often have in mind natural objects, and they want to know whether a natural object in the in the universe has a property. Okay, and we'll see examples like this, whether some natural elements are pseudo-random in some sense, are random-like in some sense. That's a typical mathematics answer, a question. And computer scientists usually, they don't care. They just want something with a property, as long as they find it. They want to, search a while and come up with something that's, you should think of this property as something good, something you would like to have. Okay, so the challenge with this situation to a computer scientist is find one. Find a strand of hay in the haystack. Okay? So find objects with these good properties, or as I said, find hay in the haystack. Now I was, looking at my slides again yesterday, and I thought that something that may have been missing in previous times I gave the talk is an explanation. People usually, when they are confronted with the question, finding a hay in a haystack, they say, what's the big deal? And the big deal is because we have the picture of a haystack in our minds or in books or where we see the hay. This is not the typical situation. Here's the typical situation. Why is it hard sometimes? Why is it hard to find hay in a haystack? Because our view of large objects may be very myopic. We may view it from a particular place. I'll show you an example. And it's not even clear that most of it is of some type, has some property. And also often, we tend because, of our experience to search using only means that we have available and maybe not the right one. So 2 examples I have here, You see this, you think it's all green, right? But we know it's not. I mean, you just have to, the way it's presented to us, we don't realize even that most of it is red. Of course, if we closed our eyes and chopped it to pieces and then took a random piece, it will be red. But that's not what we do. Another is this actually very, really interesting thing. You look at the sky and you see the stars. What are the stars? They are suns, like our sun, like the sun of the solar system. We see it because it's burning. We see them because they are burning just like our sun. And then if we want to go and inhabit places and live there, of course we don't want to live in the suns, or we can't. What we really want to live is in a planet near a sun, like ours. And until 20 years ago, it was widely believed that there are no planets, or they are extremely rare, that it's a rare property for a sun to have planets like the solar system. Why? Because we were myopic, because we searched in a particular way. Then somebody suddenly had this idea in the 90s to look a little differently at the stars. And it turns out that almost all of them do have, this wonderful property of having planets. The planets are all over the place. And rest assured, there are places to go to. Anyway, so these are just examples. But now I want to give you mathematical examples and computer science examples of these situations where you are looking for hay in haystacks, or you want to understand whether natural objects have this. So here's one example. This is an example of error-correcting code. So I don't know how many of you know, but there's these magical devices, mathematical invention that can be turned into technological invention called error-correcting codes that are supposed to handle noise in systems, in communication systems and in storage systems. Without them, all the things you have in your pockets wouldn't work. Without them, the internet wouldn't work and the clouds wouldn't work. Nothing would work. You need error-correcting codes. But not any error-correcting codes. You need useful. I'm not going to define it formally what a useful code is, but it has to have some properties. And so it turns out that you can imagine all possible codes, and within them, the codes that are useful for these applications. And it turns out it's a theorem. It's the first theorem in the subject by the person, again, Shannon, who invented coding theory. He proved that almost all codes are useful. But the proof was non-constructive. It didn't give a clue as to how to find one. So we know that almost everything is hay, and we cannot find a single strand of hay. And in fact, it took, so it's a pseudo-random property. It's shared by almost every element of this universe, but it took more than 20 years for, such codes to be found, and useful codes, and of course then they were used, and we have all these applications. So that's one example. That's a computer science type of question. Find any useful code. Here's an example of the math question. I want to define another pseudo-random property, and it's called normal numbers. So here the universe are infinite decimals, all possible infinite decimals. Do you recognize this particular infinite decimal? Yeah, Wesley, which one is it? Hi. Very good. All right. So did you check all the digits that they are? So what is a normal number? You look at an infinite decimal like this, and you start putting constraints on it. You want that it will have various, will satisfy various properties. So, for example, you would like every digit to appear the right number of times. Like 7 should appear 1/10 of the time. 8 should appear 1/10 of the time, so on, over the sequence. Every pair of digits, you want it to appear 1/100th of the time. Okay? Every triple will appear 1,000th, and so on. So there are infinitely many conditions you write down. You want all of them to be satisfied, and that's not all. You further want this to hold not only for base 10, but you want it to hold for base 2, for base 3, for base 4, for base 17, all the bases. So you write down all these infinitely many constraints. You say infinite decimal is good if it satisfies all of these constraints. And lo and behold, Borel proved that if you pick any infinite decimal like this, a real number, at random, then it has all these properties. So it's a normal number. So almost all of them are normal. So again, it's a pseudo-random property, and then you can ask yourself, okay, if you're a mathematician, is pi normal? That's a natural object, pi. We love pi. It has, we love it for many reasons. Is it normal? Or you can ask this about other natural objects like square root of 2 or e or whatever, some other numbers you know. And, we don't know the answer to this. It's an open question. So this type of questions about pseudo-random objects are hard sometimes. I want to give you 2 more examples that are much more important. Well, not important, more important than the first one, more important than this. To show you that questions about pseudo-random properties are at the heart of both mathematics and computer science. So for this, I have to turn to some major problems of math and computer science. So for the graduate students here, what is the major problem? How do you know if you got from your advisor a problem? If it's major, will it make you famous if you solve it? How do you know? Anybody wants to answer this? Of course, the answer is money. If you have $1 million reward on your problem, like this particular 7, then it's don't take me seriously. But anyway, this in the millennium year 2000, the Clay Foundation put together a bunch of very famous mathematicians to make up a list of the most important problems in math. And they came up with these 7 ones. And in this list, well, one already was solved, so you have to hurry if you want to get there. 2 of them are problems about pseudo-randomness. They are definitely not the way they are presented normally, but they are problems about pseudo-randomness. I want to know that whether P is equal to NP or not is a problem from computer science, a problem to which Dick has contributed an enormous amount of understanding. And I want to demonstrate to you that there are both questions about pseudo-randomness. So you'll see how deep this concept is. Basically, I have to define for each a pseudo-random property and show that the solution to this problem is just a solution to the type of questions I asked before. And it's very simple to do if you understand the definitions. In the P versus NP question, I will not talk about it much, but it's basically like that. The pseudo-random property is being hard to compute. So the universe is a universe of functions. Most functions are hard to compute. And we want to know whether a particular function is hard to compute, like the traveling salesman problem, if you heard about it. Or well, I can give other examples. But that's exactly like wanting to know whether pi is normal. Okay, same type of question. We don't know the answer. That's why it's an open question. Okay, so P versus NP is a question about pseudo-randomness. I will not talk much about this. I want to talk about the Riemann hypothesis. And the Riemann hypothesis, so let me put it here, but I'll elaborate on it. So you don't have to read it now. I'll explain it. Oops. I'll explain it. Then I like to talk about it, especially to mathematicians, is if the audience was math faculty in some university, the question I ask, how many people in the audience can formally state the Riemann hypothesis? I actually wonder, in this room, how many people can formally state the Riemann hypothesis? Not solve, state. Yeah, okay, 1, 2, 3. Some people are shy, 5. Okay. Actually, you'll be amazed, but even in this is like the most important, I don't know, maybe the most important, or certainly the most famous question, open question in mathematics. And despite that, maybe people are shy, but in typical math department, about 10% will raise their hand. The question of just asking to formally state the Riemann hypothesis. It's not so simple. You have to know something. But what I like to do is to give you the pseudo-random version of this question, which is equivalent, and at least to demonstrate that not only there's a pseudo-random way to capture this, but using this way of formally stating the question, you will understand it. Anybody, you don't need much background in any math. You can take it home to your family and tell them, and they will understand it too. Everybody will be able to at least state the Riemann hypothesis. I don't know about solving. So that's the last thing I want to do. Okay, so here is the statement of the Riemann hypothesis. So first I have to explain to you about the drunkard walk. So what's the drunkard walk? This is a particular street somewhere, maybe here in Berkeley. At the point 0, there is a pub. And somebody walks into the pub, has a few beers, comes out, and then starts walking up and down the street. Okay, so probably being drunk, it takes, whether it goes a step up or step down the street is a coin toss. Okay, so that's a random walk up and down the street. And you can simulate this kind of behavior. And here's a simulation of 10 experiments of what this particular drunkard would do. And it just depicts, every color just says, it goes up and down the street, and you see how far it gets from the pub. Okay? And the stunning thing about this picture is that even though it takes 100 steps, after 100 steps, almost surely it stays within 10 or 15 paces from the pub. And if it took 1,000,000 steps, it will be roughly 1,000 paces from the pub. And the general statement is that almost surely, so if these were really a random walk, a random conflicts, after n steps, it will be within roughly square root n steps of the pub. It will be sort of homebound. Of course, if you just go up, you will get farther away. But almost surely, you'll be like homebound. So because it happens almost surely, we have another pseudo-random property, right? It's held by almost all walks. Almost all walks stay close to the origin. That's good. So now let's understand whether a particular walk has this property. And this particular walk is called the Möbius walk. The Möbius walk is defined like this. First, we have to define for an integer x, what is p of x. P of x is basically, so p of x is the number of prime divisors, and using the number of prime divisors, we are defining mu of x, Möbius of x. It's 0 if the number is divisible by some prime twice, so it has a square divisor. And otherwise, we simply make it 1 or minus 1, depending on whether the number of distinct prime divisors is even or odd. Okay, that's the definition. But the important thing is that every integer gets a plus or minus 1, or sometimes 0, which we don't have to think about. So in other words, this function mu of x, this Möbius function, defines for us a walk. It says what to do, you know, whether to walk up or down the street at time 1, time 2, time 3, time 4. And we can see whether this walk stays close to the origin or not. Right? Is it pseudo-random? We can ask ourselves this question. This question was asked, and it turns out that the following two statements are equivalent. This walk is pseudo-random, so it stays close to the origin. No matter how far ahead you look, these cancellations keep it close to the origin about square root n away. That's one statement. And the other statement is the Riemann hypothesis. So in other words, to state the Riemann hypothesis is just a statement that this particular walk stays close to the origin. So you can study this problem using this lens of pseudo-randomness, and maybe it's a useful lens. Yeah.
But it seems that the property of prime divisors is the main thing in this problem.
Absolutely.
That makes it equivalent.
Yes.
So how is it really, how would you sell that this is really a pseudo-randomness problem if that's the case? Because probably with everything we can kind of build it this way so that...
So it's an excellent question. And in mathematics, in fact, having different points of view on different formulations of various problems is sometimes extremely useful because particular way of looking may have been used in another field, and you can bring techniques to work on them. You will have to, the primes will have to enter any proof of this statement, any proof of this statement. This particular way of stating it is elementary. In the other way of stating it, you need to know some maybe complex analysis. Whether it's important, it's not just a prime. Primes will be there, but whether complex analysis will have to enter this proof, we don't know. There are lots of examples where problems were solved because another angle to look into them was used. I'm not saying that this is the case here. I'm just saying that that's a way to state it.
Well,
no, yeah.
Actually, what Merton's proof was that the Riemann hypothesis was equivalent to a statement that quantity was bounded by a constant times n to the 1 half plus epsilon.
That's right.
And that's not just a pedantic point, because Mertens also conjectured wrongly that the sum was bounded by square root of n.
That's right.
And the reason why that's wrong, actually, it's strongly suspected that precisely because mu behaves randomly. In particular, it obeys the law of large, well, you know, it actually, it tends to stay within square root of n, but just like a random walk, now and then, very rarely, it gets to size square root of n log n.
That's a very good point, which the main point here is that I am lying. I'm lying to you every so often. And the reason I'm lying to you every so often is that it makes things simpler in the talk. No, the point will, yeah, if the point remains valid, I could enter the epsilon there. The point would have been, yeah, point, yeah.
But the truth is supposed to point even more than the simplified version.
I understand, but still it complicates my talk. I agree with you, but there, you know, what can I say? You are right. There is a more formal statement that is equivalent to the Riemann hypothesis, and I didn't state it. In both cases, there is a pseudo-randomness version of this conjecture. And so I want to conclude. I want to conclude just with a summary of what this viewpoint of having a subjective definition of randomness and having notions of pseudo-randomness give us in terms of the application. So that's the last slide of the talk, just summarizing. And this summarizes the really major developments in computer science in the past 3 decades. So here are the 3 possible worlds we may be living in. So there may be, the first one is a world where we have perfect randomness. Maybe quantum mechanics is correct just as stated, and maybe also we can build devices that can tap into it and generate perfect random bits for us. In this case, if this is the world we live in, then everything I showed you in the initial slides can be carried out, and this is wonderful. That's happy news, and that's the end of the story. And the question is, what do we do if it's impossible? What do we do if so the second possibility is that there are just some seemingly somewhat random, somewhat not completely, events, quantum phenomena, maybe sunspots, stock market behavior, all sorts of keystrokes, various phenomena that seem to, weather, maybe, the weather. Things that seem somewhat unpredictable, but also not completely random. Can we tap into this kind of weak random sources and use them in all the applications that we saw before? And it took about 30 years to understand, but essentially all algorithms, all algorithmic applications that I talked about are possible. And this uses what's called extractor randomness extraction theory. And the idea, without giving any detail, is that somehow you can purify randomness efficiently. You can algorithmically, efficiently take very, things that have very little entropy in them and somehow extract perfect randomness, squeeze them so that perfect randomness comes out, and then use it in algorithms. It's highly non-trivial, and that's something you can do. So even if you don't have perfect randomness, huge number of applications I talked about remain valid, so remain doable. And in fact, people are using these extractors. They are used in particular for your question about testing randomness, but I will not get into this. And the last thing is, what do we do if there is no randomness at all? Maybe the universe is deterministic, all these unpredictable phenomena are just in our head. What do we do then? Can we use any of the many applications we saw in the beginning? And here, you have to add something. You have no randomness. You have to add something, so you add it. We are going to assume that P is different than NP. I mentioned this before. I know not everybody knows what it is, but it's just the assumption that something we want to compute, like the traveling salesman problem, is a hard problem. It's just an assumption. It's a deterministic assumption. It has nothing to do with randomness. It's just an assumption that some problems we want to solve are hard. They require exponential time. With this assumption, it turns out that all the algorithms that I mentioned in like the domino counting, anything for which we have a fast probabilistic algorithm can be replaced by a fast deterministic algorithm. So even without any randomness at all, you can carry out, again, most of the applications in the slides in the beginning. And for this, there is a very important concept that you can trade off somehow hardness, computational hardness with randomness. And for this to be meaningful, you need the point of view, this subjective definition of randomness. Okay, so these are the conclusions, and let me end with this. Thank you very much. Questions? Yeah, I guess somebody told me that if you want to ask a question, you should wait for a microphone. Yeah. Even though everything is it's a small auditorium. All right? Yeah. So.
This is probably a well-recognized result, but at the beginning, when you said the depth to which you can calculate whether a population is voting red or blue doesn't depend on the size of the actual population. If the size was 200 billion or 2,000,001, you still get the exact same degree.
Yes. So again, let me state this result. You fix your desired accuracy parameter, how well you want the percentage in the sample to approximate the percentage in the whole population, and with what error bar are you willing to tolerate that it won't, right? So you want almost surely to get a very highly accurate result. There are two parameters. Given these parameters, you can calculate a number. So the parameters I used were 2% and 1%. Given these, I calculated the number 2,000. And 2,000, this sample of 2,000 is enough for any size population. The population size does not come into this theorem at all. It will work in a population of billions or trillions. It will be the same probability with the same accuracy.
But if you pick exactly the population size as the sample size, you'll be exactly right.
Yes. So now I see what it guarantees at least this accuracy, at least this. But yeah, of course, it's not, you want to get at least. In this sense, yeah, you can be even better than this, but that's as worse as you'll ever do, no matter what the population size, yes.
So even if you go to infinity, you're actually not going to exit?
Not infinity, it has to be finite, but any finite number will do, yeah. Any more? Yes?
So in your
You want to, yeah, maybe.
So you were talking about hardness versus randomness, but you didn't really take consider of another fact that random functions, random algorithms, they produce somewhat good results, but not the perfect results, right? Like in traveling salesman, if you use some kind of simulated annealing, then you wouldn't get to the best result, and in fact, you could never get to the best result using some kind of simulated annealing. So how do you take account of that in the hardness versus randomness comparison?
That's a very good question. So let me explain in just a bit more detail. Probabilistic algorithms often give, not often, I mean the point is rarely, but sometimes give the wrong results. They sometimes make a mistake. The whole point with probabilistic algorithms is that we want them to give the right result most of the time, and maybe we run it again and again just to enhance our confidence. If the problem is a decision problem, like we want to know whether a number is prime, or we want to know whether the traveling salesman tour has length 1,000, it's a decision problem, then the usual statement about probabilistic algorithm is that we want it to be correct with probability, let's say 99% over a perfect, if you have perfect randomness. You're right that there are other problems like optimization problems. Maybe it's not a decision. We want to know just what is the length of the shortest traveling salesman tour. And then we may get an approximation. Let me talk first about the just decision problems. It turns out that if the decision problem and the probabilistic algorithm that was promised, that exists, delivers the correct result with probability 99%, then it can be replaced with a deterministic algorithm, completely deterministic algorithm that never makes a mistake, never, despite the fact that the initial probabilistic one did make mistakes. So that's a part of this theorem. If it was an optimization, a probabilistic algorithm that was doing optimization, and it promised to get within, let's say, 10% of the optimal answer with probability 99%. Again, this is the type of guarantees you get from probabilistic algorithms. It was going to get you within 10% of the optimum with probability 99%. This deterministic algorithm will get within 10% of the optimum always. Okay? So that whatever guarantee you had on the probabilistic algorithm, you get from the deterministic one, if you have any hard function. Yes?
If there is no randomness, could it be still possible it would be indistinguishable from perfect randomness if it was uncomputable, like a busy beaver function modulo 2?
So that's almost exactly what hardness versus randomness means, only the kind of hardness you need is not a busy beaver kind of hard function or uncomputable function which to implement we will need to run forever. After all, the whole point here is to get results quickly. We want to simulate a fast probabilistic algorithm with a fast deterministic algorithm. That's the reason we cannot use busy beaver. But what we are using, this P different than NP assumption, allows us to use functions that can be computable in a reasonable amount of time. Reasonable in this case happen to be exponential, and I'm not explaining why exponential is enough. So the traveling salesman problem can be solved in exponential time. It's not useful for really doing it, but for this result, it turns out to be useful. I'm not going to be able to explain why. But anyway, your intuition was absolutely right. That's the way hardness is used. You use the fact that there is a hard function, and it generates for you in a certain way, using certain pseudo-random number generators, it generates for you sequences that look random to the probabilistic algorithm that need that perfect randomness. So that's what actually happens in the guts of the proof, but I'm sure it's not satisfactory to have a more detailed answer. Will take another lecture or a course, depending.
So do I get you correct that if you've got a probabilistic schema algorithm that gives you a certain percentage of the time correct value,
High percentage of the time.
high percentage,
Yeah.
then you can translate that percentage into a deterministic tolerance of like plus or minus, like this is the figure for sure, plus or minus this value.
So
in other words,
in
you're translating
optimization,
a probability into a tolerance. Is that the idea?
there is no, so in the probabilistic algorithm, there is a chance of error, which
Right.
depends on the coin tosses.
Right.
In the deterministic one, there will be no error whatsoever.
But so you've got a 10% chance of error in the coin toss.
Yeah, it will disappear.
But where it appears in your deterministic, well, let me just.
No, it will not. It
Well,
will
let me-
not come into the answer.
But does that come up again in the tolerance of the result?
No,
So the tolerance of the result is like, it'll be 5 plus or minus 0?
Yeah. So if
Okay.
let's suppose
Okay,
it was
that's
a
what I
decision
misunderstood.
problem. You want to know whether to invest in this stock or not to invest in this stock. You have a probabilistic algorithm that tells you with probability 99% the result,
it's
the accurate
yes or no.
result. Then this will be 100%. If you had the probabilistic algorithm, you'll have a deterministic algorithm, and the tiny error the probabilistic algorithm had will disappear in the deterministic one.
And then the other part is, other than quantum mechanics, a coin toss is completely deterministic. It's just that it's impossible to calculate all the forces and everything. So the randomness of the coin toss is actually really an uncomputability problem, unmeasurable and uncomputable problem. So it's not really random in that sense. I mean, is that what? I mean, it is deterministic and
so
random.
it refers to this experiment I did
I
with
wasn't
the,
here yet, I'm sorry.
Oh, sorry.
Yeah.
So we've
foot problem,
explained it.
sorry.
It's really about whether you can predict, whether your computational powers are strong enough to predict the phenomena you're looking at. Exactly, yeah.
So just wanted to clarify whether you are talking here about the property of the world, or rather a property of the model you are applying, and effectiveness in application. Because it seems that this is what you were implying before. We are talking about the assumptions that you are making the model. But you make no claim to whether the world is random or deterministic.
Absolutely. I make no claim. I have no idea how the world is built.
So this
This
are
in both
possible
is,
models, not
yeah.
possible worlds.
Well, I mean, it says what are minimal assumptions for these results to hold.
All right.
Okay? Yeah. No? All right.
So let's thank Avi for a wonderful talk.